Have you ever just looked at your phone or your laptop and wondered, how? Seriously, how does this little box of metal and plastic do all of the amazing things it does? Well, today we are going to pull back the curtain on that magic. And the goal isn't just to talk about it. Nope. The goal is to get you ready to build your very first real-life circuit. Let's jump in. Right? I mean, whether it's an old iPod or the very latest gadget, they all run on the exact same basic principles. And here's the secret. It really isn't magic at all. It's just a set of rules, a language, really. And once you learn a few of the key words, you can start speaking that language yourself. Okay, so take a look at this. This is a schematic. It's basically a blueprint for an electronic die. And right now, I get it, it probably looks like some kind of secret code, right? But I promise you, every single line, every symbol here has a specific meaning. And by the end of this, you'll have the key to start decoding diagrams just like this one. So here's our roadmap for today. We're going to start with the big question. What even is electronics? Then we'll dive into the simple rules for how electricity moves, and we'll meet the key parts that let us control it. After that, we'll see how you take a blueprint and turn it into a real thing. And then, the best part? We'll put it all together and build our first project, a blinking light. So, Section 1. What is electronics really? You know, it's so much more than just flipping a light switch. That's just raw electricity. Electronics, well, that's all about control. It's about taking that raw power and telling it exactly what to do, when to do it, and how to do it. Here's the absolute best way to think about it. Imagine a simple light bulb. You flip a switch, it's on. You flip it again, it's off. That's electricity. But now, think about adding a dimmer switch. That is electronics. See, you're not just turning it on or off anymore. You are precisely manipulating the flow of power to make it bright or dim or anywhere in between. That fine-tuned control is the entire game. Okay, so if we're going to control electricity, we first have to understand its language. And luckily, there are just a few really basic rules that pretty much explain how everything works inside a circuit. First up is voltage, and the easiest way to get this is to picture water flowing through a pipe. Voltage is the pressure that's pushing the water along. That's it. More voltage means more pressure, a stronger push. Simple as that. So, if voltage is the pressure, then what's current? Well, that's the actual flow itself. It's how much water is actually moving through that pipe at any given moment. So remember, voltage pushes and current flows. If you can lock those two ideas in, you're well on your way. Now, for any of this to happen, for that current to actually go anywhere and do anything useful, it needs to make a complete round trip. Every single circuit needs three things: a source of power, like a battery, a load, which is the thing doing the work, like a light bulb, and a complete unbroken path for that current to flow. If you break that loop anywhere, everything just stops. And that path, that loop, can be built in two fundamental ways. In a series circuit, it's one single lane. Think of those old-school holiday lights. If one bulb burns out, the whole string goes dark. But in a parallel circuit, the current splits up and takes multiple paths. That's how a big neon sign works. If one letter in your great pub grub sign goes out, the rest can stay lit. Even if you're suddenly advertising Eat Poo Rub. All right, so we've got the rules of the road. But how do we actually do the controlling? For that, we need our toolkit. Let's meet the essential components that do all the heavy lifting. We're just going to focus on the big four for now. You will find these guys, these fundamental building blocks, in almost any electronic device you can think of. They are resistors, capacitors, diodes, and transistors. Let's do a quick rundown. A resistor, well, it resists. It acts like friction to slow down the current. A capacitor is kind of like a tiny water tank. It stores up energy and then can release it all in a quick burst. A diode is basically a one-way street for electricity. It forces it to flow in only one direction. And then there's the transistor. The transistor is the real rock star. It's a tiny little electronic switcher and amplifier, and it's the foundation of all modern computers. So we have the rules of flow, and we have the parts. But how do we actually put them together? This is where we go from a plan on a piece of paper to a physical working circuit. So every project starts with that schematic, that blueprint, like the one we saw earlier. And look, I get it. At first glance, all those symbols and lines can seem super intimidating. But
there is an absolutely fantastic tool that makes translating this map into a real thing incredibly easy.
And this is it. It's called a solderless breadboard. And honestly, this is your new playground for electronics. It's designed from the ground up so you can build circuits, test them, and even mess them up and change them, all without any permanent connections or any fear of breaking something. So how does this thing work? Well, it's a block of plastic with a ton of little holes. Under the surface, there are these hidden metal clips that connect the holes together in rows. All you have to do is just push the little metal legs of your components into the holes, and boom, they're connected. It is literally plug and play for circuits. No soldering, no mess, just pure experimentation. All right, enough theory. We have covered the concepts, we've covered the rules, and we have the tools. It is time to put it all into practice and actually build something. For our first project, we're going to build the brilliant blinking bright light circuit. This is a classic for a reason. It uses several of those core components we just talked about. It shows off the idea of electronic timing, and let's be honest, the payoff of seeing that little light blink on and off is just so satisfying. So here's our cast of characters for this project. We've got a 9-volt battery, that's our power source. The brains of the whole operation is a tiny chip called a 555 timer. To control how fast the light blinks, we'll use a potentiometer, which is just a fancy name for a variable resistor. Then we have a regular resistor and a capacitor to help with the timing. And, of course, an LED, which will be our light. And the process itself? Super simple. Step 1, we're going to carefully place each part into the breadboard, following our blueprint. We'll use a few little wires to make sure everything's connected right. Then, and this is the most important step, we double, even triple check all of our work. And finally, the moment of truth. We connect the battery, and if we did it all right, we get a blinking light. But here's where it gets really, really cool. When you reach out and turn the little knob on that potentiometer, you're actually changing the resistance inside the circuit. And that change directly affects how fast or slow the LED blinks. You can go from a slow, steady pulse to a frantic strobe light. This right here is what we were talking about from the very beginning. You are now in control. So look at that. You've just seen how to go from a confusing-looking diagram to a real, working, controllable electronic device. You now understand the basics of voltage and current, you've met the core components, and you know how to put them all together. You've officially taken the first and, honestly, the most important step. So the only question left is, what are you going to create next?